has them, and today we're going to learn about arc flashes. So before I get to an arc flash, we're going to learn about an arc fault. So an arc fault is when high power discharges of electricity turn into heat, and that heat can destroy a conductor's insulation and start a fire. And these arc faults can happen when a system ages or when we reset a breaker, rack a breaker, or complete live electrical work. So the big arc flashes happen in an electrical panel typically, and it's when we've got a panel and we've got a conductor and we've got a breaker. Here's my breaker, and I've got electricity is passing through the breaker, and then I shut the breaker off, or I turn the breaker on, and that connects these two surfaces. But there's a time for when these two surfaces move together, and during that time, it's not instant, and we can, if especially if these parts start to rust and it slows down, electricity can jump from one surface to the other, and that's called an arc fault or an arc flash. And if the current is high enough, that can kill you. Now, it can happen if there's dust in the equipment. If you drop a tool inside, you gotta be careful that happens, or if you touch it with your hand. If there's condensation, if the material fails, like this can fall apart. Nothing's perfect. Or corrosion. So every electrical system has a hazard, an arc flash hazard, and the more you interact with the equipment, the more likely the risk. So removing a cover from energized equipment, installing equipment near flammable or conductive dust or hazardous environment, or having uh, overcurrent conditions where the gap between two conductors is very small. Those are uh, very high risk. So if you've got a panel and you've got two surfaces, the closer the surfaces are, easier it is for electricity to jump between them. And this jump, um, the problem is the electricity ends up in the air where there's no limit to how much current can flow, and so that energy explodes and it can melt the actual steel or copper in the panel, and that turns the copper into copper gas. So when the copper gas, when you turn solid into gas, it expands like up to 60,000 times its original size, but now it's like air basically, and that creates a pressure wave because the gas is expanding and there's so much energy. And if they got a three-phase panel, for example, then the arc flash can spread between them, and so the voltage and the current can affect the amount of energy that's released by the arc flash. So here's my example, or here's a better example. We've got two conductors here, and somebody has created an arc flash. So the electricity has passed between these two copper conductors, and a lot of things have happened. So we've got an explosion, and that's created uh, shrapnel. So some of the copper has burst as solid, and some of it has melted as liquid, which will burn you. And some of it has created a vapor cloud, which gets into your lungs. So imagine now the inside of your lungs are coated with copper, and we've got a huge sound and pressure wave. This pressure wave can throw you across the room, and the sound wave can make you deaf and probably kill you as well. it's 165 decibels, and we can end up with light and temperature of like 20,000 degrees. Now, the worse the arc flash is, and the closer you are to it, the more likely you are to get injured, and the worse injury you're going to get. So, part of the problem is we cannot get rid of arc flash hazards completely, and there's environments where there's a risk of arc flash, and the personal we're going to learn about the personal protective equipment, but even wearing the best available personal protective equipment, you can still die from an arc flash. And an arc the we can't get rid of the arc flash hazard completely, and even in an industrial facility, as simple as racking or turning on a breaker in the room, or even doing nothing, you can still have that hazard. And so, my recommendation is always to have, um, especially there's a lot of robotic systems now, and Eaton has a system that can suppress an arc flash in a main switchgear. It's something that people should look at, for example. But yeah, there's ways to reduce the risk significantly, but there's no way to eliminate it. It's not like wearing safety glasses and then, hey, I'm protected. Uh, some of these arc flash suits, they can keep you from getting burned, but they can't stop you from um, getting thrown across the room. So what we look at is the available fault current. So if we have, remember, we got our two copper lines and we got power flowing through. How much current in amps can flow through? That's the available fault current. Now, what we do is when we install a new electrical system, we must do what's called an arc flash risk assessment, which determines the likelihood of the arc flash, and then we figure out our boundary, which is the distance in feet or meters or whatever where you will be exposed to energy of 1.2 calories per square centimeter. So that's enough energy to cause a second-degree burn on your bare skin. Now, if you're closer than that, you are exposed to more energy, and if you're further, you're exposed to less energy. But at that line, you're 1.2 calories per centimeter, and that's enough to burn you. And we want to make sure. So this distance depends on the system. So a very powerful system, this might be 3 feet. Uh, a weaker system, this might be 6 inches. Now, the incident energy is how much energy your face and chest get during an arc flash, and the flash current is how much current is flowing through the air, and then the working distance will be the distance between your face and the source of the arc flash. So the duration is how much time for the circuit breaker to kick in and stop the fault. So there's got to be a circuit breaker somewhere here. We call it the code. We'll call it overcurrent device, overcurrent protective device. So this circuit breaker will detect. It won't detect an arc flash per se, but it will detect um, a very high current is flowing through it, and it'll shut off. Now that might take a second, or it might take a tenth of a second, or a hundredth of a second, but there's still a time, enough time for the electricity to pass through and kill you. So it's not like the arc flash is happening um, consistently. And if we're doing something like closing a breaker, uh, these surfaces end up touching each other, and so after a half a second or a tenth of a second or whatever, um, there's no more. Uh, there's no more. The condition for the arc flash doesn't exist anymore, unless. But if it's something like dust or you drop the tool in there, that arc flash could continue forever unless you have shut off, unless the breaker kicks in. So these are some definitions. Now we also have what we call a shock hazard. So shock hazard is just an electric shock. And again, if I have my panel, uh, we can do a shock risk assessment and then figure out what is the distance where somebody could get an electric shock, and we call that, we've got two boundaries. So the first one is the restricted approach boundary. So at the restricted approach boundary, we've got a high risk of shock, and you can come near the boundary if you're qualified and you have PPE and the insulated tools. But keep as much of your body as possible outside the boundary. And then we've got the limited approach boundary, which is further away. We still have a shock hazard, but it's lower, so we don't require PPE. But again, only a qualified person can be in the limited approach boundary, or someone unqualified who's escorted. So, and by qualified person, we tend to mean a journeyman electrician. So, uh, those are people who are qualified to be near that area. So here's a um, example. Now, so right here we are at the arc flash boundary. So if we stand right here, so here's our switch gear, and we've opened it up. Now, random office workers that are screwing around on the iPad, they don't need any PPE because they're outside the boundary. So right here is where they can get a second-degree burn. But we don't really have this. So typically, this type of equipment is in a like electrical room or electrical vault, and in some cases, the arc flash boundary extends to the walls of that room. So these people, they never get to see this equipment because the boundary is so far that they gotta be outside the room to be away from the boundary. Now, within the arc flash boundary, you can be burned a second-degree burn, which means your skin will be cooked like crispy chicken. Now, to get in here, you must have PPE, and you must be an electrician, or you have to be escorted by an electrician. So you have to wear a face shield with an LED lamp now, and you have to use the true color gray lens technology. So this is um, it's a lens. So the lens shields you from the light, that is the intense bright light that is generated by the arc flash, but it allows you to keep seeing things as if um, in true color. So it suppresses the intense bright light. Now, in order to get in here, you have to be competent. You have to have a job safety plan and a risk assessment, and you have to have a specific arc flash risk assessment, and then you must follow the electrical safety program policies, practices, and procedural requirement, and then you must also have the correct PPE. Now, if we want to get closer, we get to the limited boundary for the shock. So here you can have an arc flash and an electric shock. So even if there's no arc flash, if you're just standing there, a a a, a spark from the switch gear can kill you, or it can hurt you. So we want to avoid that. And then so we must so depending on where you are, we have a EEWP, which is or EEJSP, which is a energized electrical work permit and energized electrical job safety plan. So here, um, a office worker with PPE can be here if they're escorted by um, a journeyman technician. And then when we get to the restricted approach, only electricians are allowed here. And again, we have to go through all of the permitting and electrical safety policies, and we must have PPE to protect us from shocks. Now, the typical distance for low voltage is 18 inches, and for low voltage switch gear, it's 24 inches, and then for high voltage switch gears or motor control centers, it's 36 inches. So now when we look at the system voltage, um, anything under 30 volts, we don't care. Within the 120 volt panel, you want to be 3 foot 6 inches, and then um, if you've got a 208 to 600 volt panel, again 3 foot 6 inches gives us our shock, and 1 foot gives us our restricted boundary for shock. And then for 13,000 for anything over 600 volts, basically, um, our limited approach is 5 feet. So 5 feet. So this is 5 feet. This is where normal humans can stand. Electricians can only be within 2 feet. But I've seen transformers where the arc flash boundary is something like 30 feet. So it all depends. Any questions? Please post a comment.